So this topic is for 3.4, which is the ideal gas law. And the ideal gas law asks us to explain the relationship between the macroscopic properties of a sample of a gas or mixture of gases using the ideal gas law. So first, we have to take a minute and talk about gas pressure. There we go. All better. Okay. So gas pressure, so when we think about pressure, pressure is force divided by area. So we're looking at things colliding with another object and how much force it applies over a certain area is how we define pressure. So we are specifically looking in this case at gas particles exerting pressure on some sort of container. So if we think about force divided by area, force measured in newtons, area measured in meters squares, that gets us 1 Pascal, which is one of our many units to measure gas pressure. In chemistry, we often think about gas pressure in units called atmospheres or ATM. We can also use millimeters of mercury. We can use kilopascals or kPa. We can use bars, we can use torrs. Sometimes it's pounds per square inch, although not often because that's not a metric unit. And so we have here listed on the screen the conversions between all of these. So probably the ones you're going to use most often are atmospheres, millimeters of mercury, sometimes torr, sometimes kPa, but atmospheres and millimeters of mercury are probably the most common ones. Gas pressure is affected by 3 different variables. It's affected by temperature in T, volume, V, and number of moles in N. Okay, so those are the 3 variables that affect our pressure. When we keep 2 of the 3 constant, we can look at the effect of the other variables. So when we hold the number of particles and the temperature constant, it is an inverse relationship between pressure and volume. So that means as volume goes down, our pressure is going to go up. As volume goes up, our pressure goes down. So they go in opposite directions. If we hold number of particles or moles and pressure constant, our volume and our temperature have a direct relationship. So as our temperature goes down, our volume is going to go down. As our temperature goes up, our volume goes up. And then we also have a law where we can hold number of moles constant, and that just combines those 2 together. The one we haven't looked at specifically listed here is what happens if we hold temperature and volume present and we increase numbers. That's a direct relationship as well. And so if you hold volume and temperature constant, as you add gas particles, your pressure goes up. As you take away gas particles, your pressure goes down. All of these can be combined into what we call the ideal gas law, PV equals nRT. I personally like to call it PUVNRT. Some people call it PIVNRT. Some people just don't abbreviate it and call it the ideal gas law. So pressure is P, volume V, N is moles, T is temperature, specifically in Kelvin. So we have to use an absolute temperature scale. We can't be dealing with any negatives because then we start ending up with negative volumes and negative pressures, and that's just not a thing, okay? And then what turns this into an equation instead of just a relationship is our gas constant, R. At standard, so there's a set of conditions called standard temperature and pressure, or STP. Standard temperature and pressure is 0 Celsius. And I just realized now there is a typo on this slide. It should be 273 Kelvin, not 272. 273 Kelvin and 1 atmosphere. So standard temperature and pressure. So at STP, 1 mole has a volume of 22.4 liters. We call that standard molar volume. And so if we have that set of conditions, we can calculate what our R constant is going to be. So at 0 Celsius, 273 Kelvin, because we don't use Celsius, we use Kelvin in the ideal gas law. 1 atmosphere, 1 mole of gas, 22.4 liters. Our constant comes out to be 3 different things depending on what units we're using. Okay, so the common constants that we're going to use are 0.08206 liter atmospheres per Kelvin mole, 8.314 joules per Kelvin mole, or 62.36 liter times torr over Kelvin times moles. Now, you don't have to have these memorized. These are given to you on your equation sheet along with the equation for ideal gas law. So you don't have to have the constants memorized. You just have to remember when to use them. So you'll want to make sure that your units line up so that all of your units cancel correctly. So what units you have is going to determine what R value you use. Something else related to ideal gas law is the concept of partial pressure. So in a container, if you have a mixed amount of gases, the pressure of each individual gas added together is going to give you the pressure of the whole thing. So it's a summative relationship. Every time you add a new gas, the pressure of that gas adds to the overall pressure. So we can take this partial pressure and we can put this into our ideal gas law. So our pressure total is going to be equal to the number of total moles times R times T divided by V. So if our temperature and our volume, because it's one container, so the volume's going to be the same, it's at one set of conditions, so the temperature is going to be the same. R is always the same. Your total number of moles plugged in will get you your total pressure. When we think about these in terms of graphs, so sometimes you'll have to analyze a graph for these, we have each of our sets of conditions. So we have PV, which, like I said, is inverse, so it's going to curve. And then temperature and volume and pressure and temperature are both direct relationships, so that's going to be a straight line. And then our last one is volume and moles. So if you have a flexible container, as you add moles, your volume is going to increase because your volume is going to expand to take up more space. Same with pressure. So if you have a constant volume and you put more moles in, your pressure is going to go up in a straight line as well. So that gives us an overview of our ideal gas law. We can use this in a lot of different scenarios. We can use the ideal gas law equation like you would use any other algebraic equation, where if you know all the variables but one, you can solve for whatever's missing. We can look at this in terms of partial pressure. We can incorporate this into stoichiometry, looking at stoichiometry with gases, if gases are one of our reactants or our products. So there are a lot of different ways that we can incorporate the ideal gas law into our treatment of reactions and just chemistry.